Hi everyone, welcome to the 20th episode of Math and Beyond and this podcast. Today we are talking with Davide Biasio. He's a PhD student at the Max Planck Institute for Physics at the Max Planck Institute, and he just actually discussed his thesis on the swamp land, I think, but we are going to talk about that more extensively. Yes, geometric flow and the swamp land. We are going to talk more into that today, because today we have, let's say, a more general. We don't have a specific topic. We are going to cover multiple subjects. So I'm going to see you shortly. Bye. Okay, so here we are with Davide Biasio. I already gave a small introduction about you, Davide. You are studying, you are doing your PhD. Actually, you just finished.
Yes, that's correct.
You just, I already said this. You discussed your thesis on geometric flow and the swamp land at the Max Planck Institute for Physics. You did your Master of Science in Physics at the University of Munich, is that right? And you also studied the physics at the University of Trieste.
Mm-hmm.
Okay,
Yes.
so as I said, today we are, usually I have, let's say, sort of a specific topic of discussion with the guest, but today we are, I decided we are talking, let's say we are spanning multiple contents, because Davide has a YouTube channel, and he is doing communication of science, especially in Italian. And since he posts a lot of let's say varied and diversified content, I decided I wanted to cover multiple topics with him today. And so, fortunately, hopefully this is going to be the case. And I would like, firstly, to kick off by asking you a very, let's say, kind of controversial, let's say, question in mathematics. Do you think that mathematics is invented or discovered?
Oh, gosh. So, first of all, thank you very much for having me here. It's a great pleasure. So this is one of those eternal issues on which I cannot build a solid position. So my position has been oscillating for years, and I assume it's going to be it's going to oscillate for my whole life. Okay. Still, I started my journey being strongly on the invented side, right? I was quite constructivist when I started exploring some philosophy of mathematics. And then I perceive I kind of shifted towards some kind of slight Platonism. But yes, so I cannot answer this properly, but I assume that there might be, I would put my money on something being somehow discovered, at least some truth core or some strict dependencies or law-like statements, like as the ones we try to formulate in natural sciences with caveats. Still, there's clearly a lot being invented, right? But at least I don't know whether I would take it to be 100% invented right now. Like, I don't know whether this satisfies your question. I'm trying to be back because I have no strong opinion on the point.
Why discovered more specifically?
Mathematics is, so first of all, you have to be clear on the words you use, right? When you use the word invented, you imply a certain kind of freedom in constructing what you are inventing, right? If you invent a light bulb, right, you have some kind of freedom, which is still constrained by the laws of nature or how nature behaves. That's true. but it appears, mathematics at least, appears to be somehow constrained in a stronger way, right? Or at least leaving it on the conceptual level. I don't know how you want to characterize it, as a collection of collective mind states, or people have been trying to do this for a while. You would expect it to be less constrained than technical inventions, like than engineering inventions. You would expect it to not be constrained as them, because you do not need to realize it following your laws of nature or whatever they are. In some sense, this is not the case. Mathematics appears to be strongly constrained, right? So at least I'll think about Gödel's theorems, right? I'm not a mathematician, but Gödel's theorems tend to suggest that mathematics is more constrained as you would expect it to be if it was 100% invented in some sense, right? I mean, if you could just do it by yourself from a pure blank space, not exploiting some true in some sense, or existing structures, or existing truths, or how you want to call them, you could do without those statements that appear in Gödel's theorem, right? You could just choose to do without them. Instead, they seem to be quite solid and unavoidable in a sense, and this kind of clashes with at least a strong constructivism, I think.
Okay.
But these are vague opinions, once more, I'm trying to be, but I think I'll never get to a solid and stable opinion on this.
Okay, I understand. But I was actually about to ask you whether you thought that Gödel incompleteness theorem sort of plays a role in shaping one's own opinion whether mathematics is invented or discovered. Because at least with regards to this matter, but more, I would say more relevantly, Gödel's incompleteness theorem reminds me of when we, let's say, I recall his theorem when we try to answer a very tough question in physics, and sometimes I go like, I would say, okay, well, maybe what if Gödel incompleteness theorem also applies to our physical theories, meaning there are problems, issues in physics that we will never be able to answer because the physical theories that we have been developed have been built upon the mathematics that has been built within our, let's say, within the universe itself. It cannot be answered from outside, so from an external viewer objective perspective or something like that. So I don't know, that was something, what do you think about that?
So I think that, thank you very much for the nice question, but I think that Gödel's theorem offered not only a problem to scientists, but also a good excuse for whenever they couldn't prove a theorem, right? like
pretty much like the entropic principle.
No, the entropic principle is different. The entropic principle is different. It's clearly Gödel's theorem is serious, claiming something to be a Gödel-like statement just because you cannot prove it is like, yes, I mean, you at least need some hint towards that, right? If we want to, you can discuss the entropic principle, but that's a completely different story. As far as physics is concerned, our word appears to work, right? And that's it. So in a sense, that order, that in some sense, it appears to be working consistently, right? As far as you understand. And our physical theories are clearly mathematical structures, right? So they would in principle be affected by the existence of some, Gödel-like statement, like those that cannot be proven, blah, 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 blah. But that would have to do with the theory, the mathematical construction, not with the word itself. And that would only be the case if our mathematical constructions were consistent enough to be built from like in a top-down fashion. And at that point, you can start being worried about godlike statements, but our mathematical problems are way before that, right? I mean, our physical theories are by far not as consistent as they should be if you wanted to be worried about such niche issues.
Okay,
but that's fine, because the word purrs in the other consistency constraints. That's why physics works. Yes.
Okay, that's probably why the non-rigorousness of physics when they do mathematics.
Even here, I don't want to spread some.
I like to spread pepper. No,
prejudices, yes, but honestly, nowadays physicists do. Some of them, clearly, physicists are not all equal to each other, right? There's a lot of people doing hardcore mathematics at a very high level. There's a lot of people inventing new mathematics that mathematicians find useful and apply. So whole fields of mathematics have developed from physics at this point. The two have always been tied together. I mean, our common ancestor Newton was invented both calculus and classical mechanics. So, and the two were
while he was bored.
Pardon?
While he was bored at home.
Yeah, sure. Right. There's a few things there, but I mean, mathematics and physics have been tied together for a long time. I wouldn't say all physicists are sloppy. I would say that when you have strong experimental evidence, strong experimental constraints, you are free to be sloppier than a mathematician or sloppier than a strict theoretical physicist, because you have other constraints coming from outside. The important thing is to conserve somehow the sum of constraints coming from experimental evidence and those coming from mathematical consistency. You cannot get rid of both. In that case, you're just sloppy. But the two can compensate for each other somehow, at least as far as we understand.
Okay. And talking about physicists, you had, I think recently, had a talk with, nonetheless, Juan Maldacena. Am I pronouncing it right?
Yes.
Okay. You recorded an episode, I think, or a video with him talking about the holographic principle, if space-time could be holographic. And I would like to ask you what this guy like, because he is one of the, at least he is considered to be one of the brightest mind we really have in physics. So what is your impression? How was talking with him?
No, actually, that was not the first time, because theoretical physics is a small word. So you slowly, after a few years, end up knowing a lot of those people you had posters of in your room while being a physics bachelor's. In particular, this is one of the things I'm grateful for. Being in Munich, like at the Max Planck Institute, as you said before, we had many distinct chances of interacting with those people, right? For instance, with Maldacena himself, he came to Munich, so all of us could have long chats with them. And also, if I have to mention, for instance, the Harvard group, Wafa et al., they've come to Munich 2 years ago and stayed here for a week. And I was he dramatically, how do you call them? Destroyed me in table football, how do you call that? And ping pong. But I mean, except for these jokes, I mean, I have a few of them, but except for that, those are just normal people. Physics should really be demystified. Those are very good scientists. I mean, people with bright ideas and so on, but they are normal people. If you interact with them, you could be, you just chat. It's not more than that. And their job is trying to understand stuff about the universe. But, you know, there's a lot of, no, I don't want to disregard them. Clearly, they're extremely bright people and great contributions and all that. but we tend to assign them some kind of mystic aura, thinking that if you are in the same room as them, something happens to you when you are kind of imbued with this. I guess
your IQ starts floating higher. Yes,
that this is some kind of, I guess, pre-scientific, leftover. I totally recognize I have it too, right? And you clearly feel thrilled of being there, of having this chance of being the same. But then you realize those are people, and they do their job, and they make outstanding contributions. But they usually, as far as I have experienced, do not brag too much about it, right? I've never met someone actually bragging about it. I think Einstein might have been one constructing a whole character out of his contributions, right? Fermi wrote that in a letter once, that Einstein was that Fermi was using one of those large hats to pretend to be some kind of poet or something like that. This was written in a letter by Fermi, and in which he mocked Einstein for his attitude and all that. But I mean, those are people. They are nothing more than people doing their job. Yes. Sometimes some people are better than others, or much better than others in doing their job. Yes, that's the case.
Okay. So I would like to now ask you about a concept that always, let's say, struck me within mathematics or physics, but I think more especially without in the real world, let's say, because if I, for example, I don't know, I am in Amsterdam, if I walk with my bike over a rail path, and I look over the rail path, I will see that the path is always, not always, at least for a very long distance, is straight, and everything on the path tends to be symmetrical. And I tend to appreciate every kind of symmetries like this that I can find around the cities, when houses or whatever is nicely aligned and matched. And I would like to ask you regarding symmetries. Let's say, where can we find them within mathematics, and then within our universe more broadly?
Okay, this is way too general. Like, so starting from so mathematics has,
or let's say, the most beautiful symmetries that you believe are worth mentioning.
Okay, so mathematics has developed a few interesting tools to deal with symmetries, right? You define a symmetry as some transformation you can apply to a system without it changing whatever that means. Okay, so a sphere is spherically symmetric in the sense you can rotate it along two angles and not change the sphere as it appears to people, right? Symmetries can be preserved or broken. Clearly, if you add a small drawing on a sphere, you can then recognize rotations, and you've broken the rotational symmetry, right? This idea has been of great importance in the last century of physics development, in the sense that our fundamental theory of particles, the standard model of particle physics, is a gauge theory, which is a fancy way of saying, a Young-Mills gauge theory, which is a fancy way of saying that we take some objects, we call them quantum fields, and we make them interact in a way that preserves some symmetries, right? According to some symmetry principles. Such symmetries, once more, can be preserved or broken. And when they're broken, something interesting happens in the world. When you break a symmetry, a lot of interesting stuff happens. We can get there if you want, but and this is quite natural, right? For instance, think about, go back to a more common example. Think about what we call an Ising model. You have a lot of, which is where magnetism comes from. You have a lot of atoms, but take them as spinning balls that can either spin through an axis going up or down, right? So they spin clockwise or counterclockwise, right? And we label these two spinning directions. This is just a metaphor to make it clear, with an up or a down arrow. Okay, so you attach these to your atoms, right? And in a high temperature regime, your atoms are all spinning in the directions they like, right? They can be clearly oriented as you like, right? So they're all going, depends on the model you make, clearly, but they can all go where they like. There's no order, there's nothing, right? And so they are highly symmetric in the sense that if you move within this object, you cannot really recognize it. It's fully chaotic, okay? You cannot really recognize where you are. So everything is symmetric. If you move, you don't see any difference because everything is like the TV static, right? The white and black dots. As you cool down such a system, spins tend to align, okay? And form patches of aligned spins. So you create some order, right? Because you have chunks of atoms all spinning in the same way, towards the same direction, all arrows pointing up or all arrows pointing down or whatever. And this breaks a symmetry, right? So generally you might expect symmetry breaking because you cannot move anymore, not seeing any difference, right? You now see a difference because you can recognize it. So you can somehow connect the idea of breaking a symmetry to the idea of creating order in some sense. Or disordered systems tend to be more, this is counterintuitive, but in this perspective, disordered systems tend to be more symmetrical, right? Because you can transform them more without noticing, because they're just, right?
Okay.
Like think about a deck of cards, a deck of cards that are perfectly ordered, right? Are not symmetric. You cannot transform them. You break the order. By swapping two cards, you break the order. So that's absolutely a non-symmetric system. If you have a randomly ordered deck of cards, you can swap two and it remains a randomly ordered deck of cards. You can do a lot of stuff. And those are all symmetries if you can only probe whether your deck is ordered or not. And then there's a lot of things going on now. People think, and I tend to agree, that when you add gravity, symmetries should all be broken. You should preserve no symmetry at all. So symmetries should be some kind of left over when you take away gravity or when gravity is too weak or non-quantum. But there are good arguments to support that all global symmetries, at least, let's avoid any specific distinction, but then all physical symmetries should be broken by gravity. But this is a bit maybe too far-reaching, I don't know. Like this is at the edge of what people are doing right now. Okay.
And I think that within our universe, as you mentioned, that when you break symmetries, something interesting comes out. Don't you find that, quite ironic, the fact that the problem that there is so much matter compared to antimatter that we observe, and thus the complex life could evolve. Don't you find this due to what is I think either it was a CP violation, but I'm not sure.
Now we have to get into the details, but the people are trying to know this. Yes.
Great. This symmetry is caused to a broken symmetry. Don't you find this quite ironic? Because if we humans that appreciate symmetries, if there have always been symmetries all throughout the history of the universe, we wouldn't be here appreciating those symmetries.
In some sense, it is clear. It is clear, but I'm sure that this does not contradict what you're saying. That we appreciate symmetries for a whole other variety of evolutionary reasons. But it's quite direct if you think about it. The more symmetric you impose an object to be, the less things you can do. In general, the less you can deform it if you want to preserve symmetries, right? So the more symmetries you have, the more boring an object is.
Okay.
Because it's just as it is. It has not a big configuration space, as we would say. Like if you have a ball, right? If you drop spherical symmetry, you can deform it and pinch it and draw on it and turn it into a lot of other things. If you preserve and force your spherical symmetry, you just have a ball.
Okay.
That's quite general, I would say. So symmetries look good, but are actually bad. We do not really appreciate full symmetry, right? We never appreciate full symmetry. Full symmetry is just a huge blank space.
Super constrained
Yes, exactly. I think our aesthetic, but this goes beyond my field of, but as far as I understand, we find slightly symmetric objects pleasing. Not fully non-symmetric. You have to add just a tiny sprinkle of symmetry, but not more than that, because they get boring. So I think there's a thin line on which you have to work to find something as being aesthetically pleasing.
Okay. Okay.
But I'm not sure. Then clearly people say, okay, we've tested this on people's faces, you know, you find more handsome men with symmetric faces, more handsome and so on and so forth. Yes, but not more symmetric, strictly speaking, right? Because you do not find them handsome if you make the face like a circle and you remove eyes, nose, and mouths, right? That's so more symmetric, yes, but up to a maximum accepted symmetry.
At a certain extent, for sure. Okay.
Yes.
Okay. And you mentioned before having an object and starting to transform it. I think I can connect to this without making a huge mistake. What is a Ricci Flow? What is it, and why is it regarded to be very useful that Gregory Perelman used it? If I'm not wrong, Perelman used it in his proof for the Poincaré conjecture.
Yes, which I would call now Poincaré theorem, but except for
that's right.
But
that's
everyone
actually...
still calls it Poincaré conjecture. But yes, but it's hard now. Our funnel names stick, right? Yes. So Ricci Flow is a quite simple thing. Let me phrase it as follows. First of all, for the people listening to us, I've been working on Ricci Flow for 4 years now. I spent a lot of time on Ricci Flow and geometric flows in general. I'm not a mathematician, so I miss some mathematical subtleties, but I think we explored. You know, when a chef knows how to cook eggs and then cooks eggs in every possible different way, we kind of did the same with Ricci Flow. So we are full packed with Ricci Flow. So you know the heat equation, okay? The heat equation tells you that heat tends to spread and homogenize, okay? So if you have a sealed box with no heat transfer from outside and nothing, completely isolated from the rest of the universe, right? Which is hotter on one side than the other, the heat equation tells you that with time your heat will tend to flow and your temperature will tend to homogenize, right? Do we agree on that?
Yep.
Okay. So Ricci Flow is the same kind of intuition, but applied to the geometry. Okay. So geometric objects can be characterized in a variety of ways, including curvature. Curvature is a nice way of characterizing geometries, right? Something is either more or less curved. Okay, but we can talk about this. But as a sphere has a positive curvature. A small sphere has a higher positive curvature because it curves more. Then this can clearly be made formal. A flat plane has no curvature. An hyperbolic plane has a negative curvature, and so on and so forth. Now, Ricci Flow tends to, it's rather more subtle because it's highly nonlinear. It has a lot of things happening, but it can be seen as some kind, because it's not 100% the same, but some kind of heat equation for the curvature. So it tends to homogenize curvature on a geometric object. So if you have a sphere with some bumps and stuff, Ricci Flow will flatten those bumps. Okay? Then there's a lot of subtleties. Clearly, this works perfectly at a linear level. Okay? At a linear level, everything is fine. If you have a flat space and you perturb it, you add some bumps, some valleys and stuff, Ricci Flow will flatten them, actually behaving like a heat equation up to some diffeomorphism, as we call them. If you have a more complicated object which cannot be approximated by a plane plus some fluctuations, it will not actually properly be a heat equation. It will have other terms that can produce opposite behaviors and singularities appearing, and it's much more interesting than a heat equation.
Okay.
So you have your equation plus other terms that in some cases become less relevant. So you have approximately a heat equation, and in some others they become more relevant. So you have something different that behaves differently. Yes.
Okay. But why is it useful? Because it sounds only like a fancy tool that nerdy people that like geometry would use to do their stuff. Why is it useful for you that you do physics? And yeah, what do you apply it in physics?
For the precise reasons you mentioned, it's an interesting tool nerdy people use to study geometry, in the sense that if you want to study a geometry, so there are some objects that remain invariant under Ricci Flow, okay? Some properties of your manifolds, for instance, of your geometries, which are really hard to study as such. But if you apply Ricci Flow, your geometry becomes much more homogeneous. And those things that you know are conserved by Ricci Flow, so they cannot have changed, are much easier to assess and being studied, right? So Ricci Flow allows you to transform your problem in a problem which is much simpler to be tackled.
Okay.
Then there are physics reasons that's a very long story. Ricci Flow pops up naturally in string theory as some kind of energy dependent behavior of the graviton. But that's a long thing. If you want, we can go there. And then we applied it in refining some in constraining the behavior of, but if you want, I can tell you the whole story, but we applied it in constraining and studying features of the kind of low energy theories describing a universe you can get from superstring theory, okay? So to connect it with our phenomenology with the standard model and such. And in this scenario, Ricci Flow appears to be quite useful. Yes.
Okay. Just one quick thought that I had right now. We know that black holes are huge warps in the space-time manifold, right? Is there a way to use, or has it ever been used, Ricci Flow to model those warps, to model those holes in the manifold, such that, let's say, because we know that at the singularity, the manifold, our manifold basically breaks at the end. It appears not to exist anymore because it's in some quantities of Einstein field equation goes to infinity. Is there a way to apply Ricci Flow to black holes, and more especially to the singularity of a black hole, to kind of reconcile our manifold, said bluntly?
You cannot apply Ricci Flow to a singular point, as always, because that's the usual problem. But that has a lot to do with physics. We know black hole singularities are not there. That's a signal of general relativity breaking down. So there's no problem with that. We just have to discover how to solve that. But I guess that no one expects a singularity to actually be there and to actually be a problem. Surely there are techniques to deal with flow singularities, but that's a whole different different point. When Ricci Flow can create singularities, right? Not cure them. It's a differential equation, so it cannot transform a singularity in something which is not singular in any way, because it's not defined at the singularity.
How can it create? How can Ricci Flow create singularities?
Well, you have a geometry and you deform it, and for many reasons, I told you there are other terms, not only heat terms. Your geometry can pinch, right? It can shrink and pinch. So effectively, you create a singularity at the pinching point. Imagine you have this kind of object, which is thick, right? With a neck, some kind of neck, two balls connected by a neck. There's a variety of settings in which the neck shrinks and pinches, right? So you effectively create a singularity. And you have to deal with that properly mathematically. What Perelman did was introducing some surgery techniques, namely before hitting the singularity, you stop your flow, you cut, as a surgeon, the singularity away, you remove it by 2 smooth caps, and then you allow your balls to flow distinctly and separately. So you actually remove the portion of the manifold which is pathological, okay? And you go on with the flow.
Okay, this is very speculative thought that I'm giving you, so take it in Italian we would say con le pinze. What if this is precisely, not precisely, but let's say analogous, let's put it this way, to what happens at the singularity of a black hole?
This cannot be analogous to what happens at the singularity of a black hole, because we, strictly speaking, we expect a singularity not to be there, right? Not a singularity appearing and then being removed by someone, okay? You cannot have this cosmic surgeon entering black holes and removing singularities, substituting them with smooth caps. What people have done instead, so this is not a good model of a physical process, clearly, in itself. So if that's your question, people have used these techniques, and that instead is completely fair to create some kind of toy models of interiors of black holes, right? So instead of studying the physical process that governs the high curvature region inside the black hole, you just cut it off and remove it with a smooth cap, and that's it. But that's not a model of a physical process. That's interesting. That allows you to make some deductions, to make some claims, to constrain how this can be done, and so on and so forth, blah, 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 blah. But as a matter of principle, this is just skipping the whole singularity resolution procedure. It's a placeholder for an actual physical process. Maybe that connects to your question.
Okay. Now I would like to let's say connect to the, hopefully again here I'm not saying something wrong. When you previously mentioned when you have a small sealed box and you have a part which is hot and one other which is called the process of the molecules being more uniform, being more uniformly let's say warmer in the box, is related to the concept of entropy. If I'm right. And I would like to ask you, what is entropy? And I would like to ask you first from let's say from the point of view of statistical mechanics, how statistical mechanics deals with entropy, and second, how thermodynamics deals with the concept of entropy.
But so the two are not different, first of all. Like thermodynamics can be seen as a historical effective theory of statistical mechanics. So once you land on statistical mechanics, you don't really need thermodynamics anymore, right? I mean, it's just an effective theory you can apply. I mean, you can derive thermodynamics from statistical mechanics. So it's not, thermodynamics was an experimental research program which converted some, no, it's not a joke, like they were observing some, pardon?
No, I believe it. It's weird because of courses in thermodynamics at the universities.
No, yeah, sure. But it was like, let's not say only experimental, let me use the word, a phenomenological research program in which they were doing a lot of experiments and observing some fixed ratios and fixed behaviors of some observables, some stuff you can measure, temperature and so on and so forth, defined as that thing you measure with a thermometer and so on and so forth. And they related them with some laws. Okay. This missed a fundamental picture, clearly. That came with statistical mechanics. Statistical mechanics allows you to derive thermodynamics precisely in that sense. You have some fundamental description of an object, which is microscopic, from which you can derive a macroscopic picture then, under the assumptions of working in the same setting in which the thermodynamics people used to work, gets you to thermodynamics. So in a sense, statistical mechanics is much more fundamental. And in that sense, entropy is defined in a very simple way. So it has to do with the way in which we connect a macroscopic and a microscopic description. So let's say you're studying some kind of physical system, okay? And of that physical system, you can measure some macroscopic observables, as its temperature, for instance, or its color, as you see it, or whatever, its smell. Let's take it as you like, right? I make it funny in general, but strictly speaking, this can be made formal. But you can only measure these macroscopic observables, okay? So that system will have some microscopic description. For instance, a gas will ultimately be described as a collection of moving gas particles. Okay?
Mm-hmm.
And to the same macroscopic configuration, okay, there's a huge number of equally valid microscopic configurations, right? If you have the same temperature and the same macroscopic observables like volume, pressure, temperature, and so on, you have a lot of room for wiggles at the level of the microscopic description, right? You can move a single particle without changing the temperature. You can swap two particles without changing the temperature, the volume, the pressure, and so on and so forth. You can do a lot of stuff. So the resulting perspective is that there's a huge number of microscopic configurations that are equal from a macroscopic perspective. Okay. Entropy precisely fixing your macroscopic perspective counts the number of distinct microscopic configurations that can give you the same macroscopic configuration. It counts them with a logarithm, but that's purely technical. And in this sense, we say that the entropy is higher when your macroscopic configuration can be realized by a higher number of microscopic configurations. Okay? And it's lower when you have just a few distinct microscopic configurations that can realize your macroscopic configuration. And in this sense, if you assume your and it is a strong assumption, but if you assume all your microscopic configurations to be equally plausible, to have the same assigned probability, okay, it is natural that your macroscopic system will evolve towards higher entropy configurations, right? Because statistically, those are the ones realized by the higher number of microscopic configurations, right? If they're all equally plausible, then you'll usually land and probably land in the higher chunk that corresponds to a high entropy macroscopic configuration. This is entropy, nothing more than that.
Okay. And why a fundamental concept like this one is related to the other fundamental concept, which is the arrow of time?
Well, this is, I guess this is still to be understood. This is still to be understood. People have argued that this thing I mentioned, right? The fact that at a macroscopic level, this entropy appears to be ever growing under a few other assumptions and so on and so forth. Kind of signals an arrow of time. So in a sense, the idea is the following: your entropy grows, and you define your arrow of time as that direction in which entropy grows. Okay, I'm not convinced at all by this. Honestly, I don't buy it. Even if you phrase it properly, I think that in the end it ends up being circular. I cannot avoid thinking it ends up being circular. And there's a lot to be understood yet about maybe there's something clearly. I think that Ravelli and his people somehow phrased this in an interesting way in one of the books. I think in they worked on this idea of defining the arrow of time with some macroscopic observables, but this meshes with this perspective of not having time at a fundamental level and so on and so forth, being it an emergent property. I think such a problem, which will become clearer when we'll have a full theory of quantum gravity. And once we have that, we can settle the problem of the arrow of time. But until then, it's quite hard, because that still is tied to the causal structure of a universe, to a geometry. And until we don't know, until we don't actually understand how it comes to be, it's quite hard to solve all the small problems. Okay. It opens a lot of doors, or a lot of questions we are still not able to phrase properly, like, okay, how does our brain attach to this arrow of time? Why do we perceive an arrow of time? Why do we blah, 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 blah? But these are like still confused and vague questions. This is stuff people are working on. Yes.
I have seen, I think kind of recently, a video of Sabina Hold. I don't remember. Yes, I can never remember the name. The last name. She was talking about entropy, and she basically kind of said that we are not completely sure, because we know that entropy can always either stay the same or increase. That's the second law of thermodynamics, right?
That's the statistical statement I mentioned before. Okay.
And she said that we are not completely sure that in the early universe, entropy worked the same as it does now. What do you think? What do you think about this? And if so, what do you think would be different about entropy in the early universe? Because if entropy is related to our arrow of time, and we say, okay, but maybe in the early universe, entropy may have been working in a different manner. What do you think could be going on at the time with regards to entropy?
So
and the arrow of time?
Once more, I do not think entropy is that much related to the arrow of time at a fundamental level. Okay, we see something that grows and we take it seriously enough to say, oh gosh, that's the arrow of time. Okay. I do not want to mock the serious versions of this proposal, clearly, but honestly, it never appeared. When scraping off all the things you can add to this, it never appeared to be much more than this, to me at least. Maybe I'm not understanding something. So I think the arrow of time will be solved by it, because then I don't know what this would imply. Like, if entropy fluctuates in a finite system, does this mean that the arrow of time fluctuates? But does the arrow of time fluctuates every time a particle, for some reason, randomly goes in the gas concerning the gas content of this room? Whenever, for some random reasons, which is highly unlikely, but can happen, particles arrange in a way that for some time has a lower entropy content or whatever. Does this mean time is going backwards? I mean, I don't fully buy it, I'm being honest. Plus, thermodynamics enforces you to take a lot of limits. So it's not 100% clear how to apply said reasoning to the whole universe, right? It is not clear. We are still not able to write a theory for the whole universe. We do not know how such a theory would work. We do not know. Our theories have the notion of performing a measurement built in. So it's not clear how you should perform a measurement on the whole universe, right? So there's a lot of attempts in trying to solve this. I think that in order to make this question clearer, we would need at least two ingredients. First of all, a theory of quantum gravity. That's absolutely crucial in understanding how time might have worked in the early universe. Okay, so first of all, in the very early universe, right? Because after a while, it is quite clear how things worked out, except for at least space-time wise, right? We have inflation, or we have to settle it, but we do not expect some weird quantum gravitational phase transition to appear, at least. I mean, it depends on where you set the bar, but we're only talking about the very, very, very early universe. So we totally need a quantum theory of gravity, because without that, we cannot treat space-time at the microscopic level. So there's no point in guessing. I mean, I can guess, and on top of that, we need to perhaps properly understand quantum mechanics and provide us with an interpretation of the theory that allows you to get rid of measurement or to understand how measurements come to be. And that's a whole other problem. But I think the two problems are tied together and they're needed in order to address such questions. So that's quite important.
Okay. Regarding quantum mechanics, I would like to ask you, what is the meaning of the very famous Planck's constant? Why did such a constant arise? What's the meaning of this number?
Well, the Planck constant is a constant, first of all, that appears in our equations and somehow tunes, as any other constant, tunes some effects. It's not magical, right? As the gravitational constant tunes the strength of the gravitational interaction, as the Coulomb constant tunes the strength of the electrostatic interaction in classical electrodynamics and so on and so forth. The same applies. The Planck's constant is a bit different because it's not as those coupling constant, but it tunes somehow the quantumness of your system, right? So it allows you for a transition from the quantum to the classical, right? Your physical processes can be characterized by something you call an action, right? It's a real number you assign to a physical process, okay? Whatever that is, it's not so important. The action is measured in the same units of Planck's constant, okay? So the ratio is a pure number with no unit of measurement. It's an actual ratio, okay? And when your action is comparable to Planck's constant, more or less, allow me to be sloppy here, you can expect quantumness, right? Usually, this might be a way of seeing it. So it tells you, this can be seen in a variety of ways. Planck's constant controls the way in which energy levels get discretized in a given system. Planck's constant controls the way in which energy is associated to the frequency of a photon, for instance, of a massless particle. Planck's constant controls the way in which different classical trajectories overlap in producing a quantum process. And if you send it to zero, if you take Planck's constant and you send it to zero, you remove all this quantumness I mentioned. That's not really always the case. You need to do other things, but that's some kind of general intuition. Okay.
What instead is the, which I think related again to the Planck's constant, what does Heisenberg uncertainty principle say? What is this principle about?
Well, Heisenberg uncertainty principle tells you more or less that there exist couples of observables that cannot commute. Observables are the things we measure in nature, okay? Things we can measure, like the position of a particle or its momentum, its velocity, right? And before quantum mechanics, we were sure that measuring velocity and then position, or position and then velocity, would have been the same, okay? Heisenberg's uncertainty principle simply tells you that this is not the case, taken at face value. You produce different outcomes by performing the measurements in opposite order, right? This is it at the very base level.
Okay. So how is the Planck's constant related to this principle?
Well, it controls the amount of non-commutativity among the two observables in this sense. If you send it to zero, the two commute. You can measure them in any order.
So basically, what this says is that at a very microscopic level, very microscopic level, we don't really know what is going on with certain precision, meaning the standard deviation of the measurement that we make.
No, be careful. This does not imply only that we cannot measure stuff. Okay, that's not the only point. Quantum mechanics tells you, then you might suggest that some other fundamental theory might restore this classical intuition, but you have to give up, for instance, locality, but we can get there. But at this stage, we only have quantum mechanics. It appears to be extremely solid. it appears to be dramatically solid. It works in model building quantum fields and predicted particle masses with a super strong precision at super high energies, and it predicts magnetization and phases of matter and cosmological perturbations. Like quantum mechanics is absolutely super solid. And that theory tells you not really that you cannot measure stuff, but that notions such as position and momentum might not be defined themselves at the microscopic level. Okay?
Okay, so we don't really know what is going on. We can describe it probabilistically.
No. You can describe it. You have an object, but for instance, that's not so surprising. Like there's a whole bunch of macroscopic properties that lose meaning at a microscopic level. For instance, think about water. Water can be water, ice, or vapor, gas. Okay? If you look at a single molecule, if you zoom in and you look at a single molecule, this notion of phase disappears. Water molecule is just H2O. So asking whether that molecule is liquid, solid, or gaseous is a meaningless question, right? That's the point. This happens a lot of times in nature. For instance, if you have an extended object, okay, take this object, right? If you look at it from far away, it looks point-like. Okay, so it has a definite position defined by 3 numbers. Okay, X, Y, Z. If you look closely, it is not a point anymore. So you cannot define its position. Trying to define its position with 3 numbers becomes meaningless. Okay, so there's a lot of things like this that happen in nature. In particular, what quantum mechanics appears to be telling you is that your macroscopic notions, position, momentum, such concepts you developed by evolving in a macroscopic world, trying to survive from wild animals and so on and so forth, do not strictly apply to the microscopic world. Instead, we have to apply another set of concepts that we developed with quantum mechanics that work perfectly well. Now, the point with understanding quantum mechanics is that it does not fully constrain the way you can interpret said concepts, right? Namely, there are equally valid, distinct interpretations of quantum mechanics. Okay? So that's a thing. In that sense, there's still some room for understanding, meaning you can interpret it in distinct ways. And we have experimental evidence. I mean, no, we have experimental certainty, because this is really theory independent, that in order, if you'd like to restore your classical notion of position and momentum at a fundamental level, okay, we call this or all other variables. If you want all your variables to be defined, okay, we do not know whether this is possible, whether you can write an alternative theory that has this content, but we know that said theory cannot be local, okay, cannot satisfy the principle of locality. We have a no-go theorem. If you have locality, you have to give up on reality. Locality is that thing for which close things affect each other, and there's no large distance random correlations or any correlation like which is non-local, actually. Things interacting at different points as they usually interact closely, right? If you want locality and some other assumptions, just a few people think the other assumption can be dropped, like statistical independence, but let's say locality. If you want, there's 3 assumptions actually, but let's set one aside for the time being, which is statistical independence. If you want to have a theory that respects your classical realism, namely, things have well-defined properties, blah, 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 you have to give up on locality. That's it. Because a world in which you have both locality and reality and if we want statistical independence, but that's just technical. I would leave it aside. If you have reality and locality, your word must satisfy some laws, okay, regardless of the specific framework you want to, must satisfy some inequalities, right? Correlations among different experiments must satisfy some inequalities, which are called Bell inequalities, okay? And we know experimentally that a word does not satisfy Bell inequalities. Our word, not quantum mechanics in itself, our physical word. So our word is either non-local, non-real, in the sense of realism as you mentioned it before, like things having defined properties, or neither local nor realist, plus that third assumption we have. Quantum mechanics is the choice of preserving locality and dropping realism, okay? In this sense, it's not like it's not real. That's a very bad word that seems to suggest something more, but keep it as such.
Yeah.
Quantum mechanics goes that way, and it has proven that going that way, you can go really far, dramatically far, okay? People have been trying to do the opposite, like to preserve realism as you appear to like, and drop local principle of locality. As of now, no one has managed to reproduce quantum field theory properly. Like you can construct some things that honestly, personally do not look good at a conceptual level, but that's personal bias. But the fact is that you can construct things that replicate quantum mechanics. Okay, you can do that, which are local, non-local and realist, okay, in which things have definite properties by giving up locality. But as far as we understand, we still cannot, and it might not be possible at all. We don't really know that. We might not be able to push it to quantum field theory, namely merge it with special relativity, right? I personally think that it is really important for someone to be working on this, right? To the option of constructing a non-local realist quantum field theory. I think it is crucial for people to do it, okay? Because knowing that we have an alternative would be awesome. Or getting convinced that we cannot have an alternative due to it being too hard would also be important and awesome. But as of now, we have to admit that the only path that led us really far away is the local non-realist path. One might desire to drop also locality for other reasons, but then you go beyond. But still, I think it's worth pursuing the alternative. Sure, that's not. I would defend this position.
Okay. This path of the quantum of this quantum theory has led us also to some problem. Let's say one of these is the so-called quantum entanglement. What is this issue that we are having? What is that we are not understanding about quantum entanglement? And what are the implications of this issue?
No, pardon me. It is usually phrased as a problem, but it is not. Like quantum entanglement is a feature that quantum mechanics predicts. Okay. There was a paper by Einstein, Podolsky, and Rosen in which they showed entanglement. And they said, you see, you have this entanglement. Then I'll tell you what it is. But it's a very weird thing, so your theory must be wrong. Okay. Then we made experimental tests and entanglement is there. So it's not a problem. It was originally phrased as a problem because their claim was, you see, you have entanglement. Your theory cannot be realist, right? Because you have entanglement. That was exactly the point at the beginning. Or it can be realist only in a way that defies special relativity because it breaks blah, blah, blah. But since Einstein wanted both locality and realism, so Einstein wanted both locality and realism, right? Then we can get into the details of these words, but whatever they are, he showed that quantum mechanics predicted entanglement. So his argument was the following. A word cannot be non-local or non-real. So quantum mechanics, roughly, must be wrong because it has something, we call it entanglement, that defies one of the two.
Okay.
Okay. Then we found entanglement in the lab. So our word has entanglement. And that's it, right? So it's not a problem. It's a feature we understand, quite easy to understand, honestly. And it is puzzling at a philosophical level, not at a physical or technological level. We are now using entanglement to construct a lot of technology. So it's like all the quantum computing business is based on our understanding of entanglement. So we can make it in the lab, we can model it with a theory. So we can model it with a theory, we can reproduce it in the lab, and we can construct the technology with it. I wouldn't call this a problem.
Okay.
It's something, it's a feature, a weird feature of nature, which does not display which is not evident at the macroscopic level. So for us, it's puzzling. So we have to somehow match our philosophical concepts to entanglement, okay? But except for that, it's a well-defined feature of nature. And it has to do with systems being more correlated than you would expect from classical mechanics, okay? More or less from, then we should go into mathematics, but assume you produce two photons, okay, together in a so-called entangled state, whatever they are. But if you have two photons that share some entanglement, okay, and you bring them far away from each other, right? You perform some measurements, which cannot influence each other because no signal can travel faster than the speed of light. And you make such experiments in a way that you do not allow anything to travel between the two. So the two experiments are actually independent, okay? You do this a lot of times. So you make some statistics on your two experiments, on one side and one on the other of this, on these couples of entangled photons. And among your experimental results, you find a correlation, okay, which is much stronger than any correlation you can have in classical mechanics, okay? This is the idea. So quantum systems that are in entangled states correlate more than you would expect from your classical intuition. And this allows you to do a lot of stuff. For instance, perfect cryptography, or cloning, quantum cloning of quantum states, or key distributions, and so key distribution and so on and so forth. Quantum computing, or all that stuff comes from there, comes from our understanding of entanglement. Yeah. Before I mentioned Bell's theorem and Bell's inequalities and the experiment, that's precisely the thing, right? Einstein, Podolsky, and Rosen came up with this entanglement. Bell showed properly that locality plus realism in Einstein's sense implied some inequalities. Then people started testing it. Last year, people got the Nobel Prize for this, Clauser, Aspect, and Zeilinger. And they actually tested that Bell's inequalities are violated. So entanglement appears to be fine with a word. That's it.
Okay. How did we find it experimentally?
Exactly as I described. The kind of a more precise experimental setup, clearly, but the fundamental idea is to have some source emitting photons in an entangled state, whatever that is, at a quantum mechanical level, but having entanglement according to quantum mechanics, and then performing measurements, independent measurements on the two photons at very large distances. This is technically quite hard because you have to preserve entanglement. You do not have your photons interact too much with the environment, or you want to avoid them interacting with the environment. Otherwise, they would spoil the state. You want to preserve the initial state of the photons somehow, or some features of their initial state, clearly. And then you perform these measurements, and you compare the results, and you study correlations among them.
Okay.
For instance.
Okay, I just want to ask you why there was I think I've read from Hawking, or I don't remember who, there was some debate that quantum entanglement, I mean, people were discussing and saying, this is controversial, because people were saying, okay, but then quantum entanglement allows faster than the speed of light travel. Why this is not the case?
The people thought that at the beginning. That's a natural guess you can make. Because if you have an entangled pair of photons, right, you perform a measurement on one of the two. And even what quantum mechanics tells you is that even at extremely large distances, whatever they are, the state of the other photon changes because they share a common state somehow, right? I too would like this picture to be substituted by some physical process, but I think we would have to go beyond quantum mechanics for that. But still, as far as we understand, this is what happens. And people started questioning, okay, but if I can manipulate one photon and affect the other at an arbitrary distance, I should in principle be able to communicate a signal with this, effect. So I would effectively be communicating a signal faster than the speed of light. In this sense, this is quite miraculous. This is one of the reasons for which quantum mechanics gets to be convincing. You show by doing your computations that no signal can be sent this way. You can transform the state of the other photon, but in order to send an actual signal, like to send some bits of information to the other person doing the other experiment, you need also a classical communication, which is subject to the limit on the speed of light. So, pardon?
Oh, okay, I said I understand.
Yes, so in that way, since you also need a classical communication, you're perfectly subject to the laws of special relativity, nothing is broken, which is quite interesting in itself. Because somehow quantum mechanics, despite having these large distance correlations, shows you that such correlations cannot be used to transfer signals. So that's quite cool. Because in order to somehow read off your result, you need to know what I measured on my photon, what I did on my photon. And this can only be communicated classically by me picking up my phone and telling you, okay, I did this and this and this. So in that sense, there's a strong constraint. And you can show this in general. Yes, you cannot use entanglement to communicate stuff.
Okay. I would like now to cover the so-called measurement problem, and which is sort of tied to the intricate concept of the wave function in quantum mechanics. First of all, what is the wave function? And let's say, second of all, why do we have a so-called measurement problem in our quantum theory?
So the way we describe quantum systems is the following, okay? You have a physical system. Said physical system can be many different configurations, okay? For instance, a particle can be many distinct positions, okay? And in quantum mechanics, instead of using the position of the particle, or more in general, the configurations of your system as a fundamental dynamical object, you instead use some kind of probability density over the configurations of your system. So what you evolve in time is not the position of a particle, but some function of the position of the particle, which is a probability density, something that when squared is a probability distribution. Okay, you need this. You cannot use a probability distribution because we observe some interference patterns in quantum mechanics, and in order to achieve them, you need a probability density, not a probability distribution, right? Now, what is that object? We call that wave function. So first of all, that's not an object defined on spacetime, right? It is an object defined on the space of configurations of your system. When the configurations it's not like the electromagnetic field, which is a function of space and time that tells you, when you give me a point in spacetime, that tells you the value of the electromagnetic field. It's not the same thing. But if you have a single particle with this position, your wave function is a function of x, y, z, yes, and time, yes, that looks like a spacetime function. But if you have two particles, your wave function is a function of x1, x2, epsilon, y1, y2, z1, z2, the positions of both particles, right? So it really lives on your space of configurations, right? And depends on time, okay? is that object physical, or is it just a placeholder for some more fundamental object? Okay, so does it express a physical intrinsic probability of the word, or does it describe a lack of knowledge on some more fundamental object that does not involve probabilities, which is the thing we were mentioning before? We still do not know, but finding a more fundamental theory that gets rid of wave functions would be what we said before. You would have to get rid of locality, and even by doing so, it's quite hard to do it in a natural conceptual way without introducing other weird objects, right? But still, like, taken as such, as far as we understand, the wave function is the fundamental object we can describe and make physics on with an extreme precision, okay? And there are good arguments for it not be some kind of just epistemological object, just labeling our ignorance. There are very strong arguments for that, and being actually a physical object. But what is its collapse? So within quantum mechanics, when you perform a measurement on a system, for instance, the position of a particle, the wave function assigns a probability to each possible outcome of said measurement, okay? You cannot know stuff for certain when you measure your observables. But when you perform a measurement and you find the position here, your wave function concentrates at that position because you now have a definite position because you made the measurement. So in this sense, the wave function is spread before you perform a measurement, and when you perform it, it collapses on the value you've measured, and then it starts spreading again. Okay, is this a physical process? Does it only have to do with our ignorance? We don't know. As far as we understand, we have no fundamental alternative theory that can be made consistent with special relativity in which this is only epistemological. Okay, there's also some interpretations of quantum mechanics that tell you that it is epistemological. Okay, it has to do with our knowledge of the word, but that's the only thing that actually exists. So there's some interpretations of quantum mechanics telling you that the wave function labels the ways in which one subsystem of the universe somehow interacts with another subsystem of the universe, and that's the only thing that can be said about the universe at all. Okay, and that's all of what reality is made of. But we are going a bit beyond that. By quantum gravity and so on and so forth, but they are totally legit. And there's a huge variety. I mean, I don't want to push it, but for Italian speakers, I spent 30 hours doing lectures on this issue, on distinct interpretations of quantum mechanics on YouTube. So those can be found there if you want. But so in this sense, the collapse of the wave function is precisely what happens, how you model the measurement process. Okay. There are people trying to turn the collapse of the wave function into an actual physical process, okay, by modifying quantum mechanics. One notable example is Girardi, Rimini-Veltman, GRW, okay, which was developed by a few people, in which the collapse of the wave function is an actual physical process that happens and becomes more plausible when you perform measurements and so on and so forth. But then, I mean, those are called spontaneous collapse models and so on and so forth. And this has to do with the way we model measurements. That's still the big open question in going beyond quantum mechanics, and which might be needed when trying to apply quantum mechanics to the universe. Okay.
Instead, you mentioned that we have different interpretation of quantum mechanics, and I would like to ask you, can you expand on this interpretation? What do these interpretations say different than each other? Why do we even have different interpretation of quantum mechanics?
The last question is quite natural. Quantum mechanics is a mathematical system that works, a mathematical construction that works really well in predicting experimental outcomes, but it defies our classical intuition, right? So at that point, you need to build an intuition. And the thing is that you can build multiple alternative intuitions on the same mathematics. But this is the same, applies in the same way to classical mechanics, for instance. The point is that there we have a built-in intuition. So we never question the correct interpretation of classical mechanics. But I'm sure you can cook up many distinct interpretations of classical mechanics. We only chose the natural one that connects with our everyday experience, right? With a naive realism and human experience, right? Quantum mechanics does not allow us to do so, to single out a specific interpretation as more natural, more connected to our experience. So we have to cook up one. That's a big problem. But a theory constrains a lot the kind of interpretations you can have. And honestly, the main distinction between them is the one I mentioned before. Ontic interpretations of quantum mechanics, in which you take the wave function to be an actual physical object, an actual thing, okay, and draw the natural conclusions from that assumption, okay, consistent with all we know about the world, or the so-called epistemic interpretations of the wave function, in which you take the wave function to be a placeholder for your knowledge on a system, and you take the consequences of that assumption. And then you find a huge variety of distinct interpretations that make different assumptions along the way to fill the gaps. And then you find yourself with a huge plethora of distinct interpretations that I don't know whether they exhaust, and I don't think so, the possible ones, but they sure tell you of something about quantum mechanics. I think that when you discover that a theory you have can be interpreted in distinct ways, you are learning something about the theory. You are seeing it more clearly, right?
Okay. So
it's like you have the drawing, pardon me, of what is a duck and a rabbit, right? The drawing is there. You know it, that if you look at it in one way, it looks like a rabbit. It's a Gestalt.
Okay.
You can see it as a rabbit, as a duck. The drawing is the same, okay? But when you understand that it can be seen either as a duck or as a rabbit, you learn something about the drawing. I think more or less the same applies to interpretations of quantum mechanics.
Okay. So basically what you were saying also before is that regarding the wave function, yeah, some people believe it is a physical object, some other believe it is not it's not an object in our universe, it's not a physical process. So at the end of the day, we cannot, or let's say, can we measure it physically, or can we only do computation and calculation using the wave function?
Well, when you perform, the point is that within quantum mechanics, when you perform a measurement, you have this collapse of the wave function. So you cannot observe a wave function without making it collapse, okay, within quantum mechanics. We are not at a stage in which we can conceive experiments that might work differently. Clearly, I don't know what lies in the future for us. Maybe we'll find ways of testing distinct interpretations of quantum mechanics, making different predictions, or maybe finding, this is my hope, that one of those interpretations will be much more naturally consistent with quantum gravity. That's my hope, okay? So, and there are signals pointing in that direction, or at least pointing at some of them being quite in clash with quantum gravity. And so in that sense, if you have a new theory that works really well, that matches precisely with one of your, and nicely with one of your interpretations and not with the others, maybe you put more fishes on that. That's the kind of thing we might do. Single out it with other physics, so not by direct measurement.
Okay. When you, I would like to ask you, maybe this is more personal. When you work on some new, let's say, yeah, you try to understand more, you try to wrap your head around some physical theory, you try to dig more in our domain of knowledge and understanding the universe. What do you think the meaning of this all is? Meaning everything comes from a bunch of right, matter. Everything that we see comes from a bunch of matter that have been evolving throughout the history of the universe, such that complex life that could auto-replicate itself and could evolve into such an intricate thing, which is our civilization, which can understand its surrounding. because we know that there are many other living things in our world, but they do not have our knowledge. They cannot contemplate the inner working of all of this. What do you think? Does it feel strange to you when you study? Maybe also you go back in time trying to study the origin of all of this.
First of all, I make no assumption on the consciousness state of other living beings. There's a huge debate on this, so I don't know. I don't know. I think many people could argue that at least an octopus or some other animal of that kind has some degree of consciousness, but I will not get there. Then things get weird and philosophers start asking, okay, well, if we compare a newborn human and an adult octopus, a particularly intelligent adult octopus, what, I mean, you know, philosophers, how they go into those rabbit holes. So first of all, since we developed theories of automata, of, you know, all the time in which people started studying chaos and order and complex systems and so on and so forth, this problem of life emerging from fundamental interacting objects got quite demystified, right? We found a huge variety of distinct mathematical models of complex behaviors emerging from very fundamental interacting objects, given enough time and enough energy. Remember that the Earth is not a closed system. It's constantly bathed by sun's light. So we are a system with a huge energy intake that allows you to, you know, defy all these entropy things and so on and so forth. So we are not an isolated system. And in this sense, at an intellectual level, I do not find the existence of life and so on and so forth disturbing. I find it strange. There's a clash, clearly, because anyone remains a human. So even if at an intellectual level, I understand that this is completely plausible and perfectly reasonable, it is quite a different thing to feel it in your bones, right? And as a human, I keep perceiving this strangeness. You can, even if at an intellectual level, you convince yourself that there's nothing magical behind it. Your personal experience is another thing, and it's equally valuable, I would say, or more valuable, as that's what characterizes your existence in this universe. So at a personal level, yes, I do find it miraculous, strange, weird, inexplicable, mysterious, magical. Again, but these are two, I think, different. It's quite hard, and I wouldn't even like to. I mean, those are two distinct realms of inquiry, I think, equally that require to be equally dignified in a sense. So on the other hand, the more we get into, I think that physicists nowadays have learned how their intuitions can be defied. Okay. So at the beginning of the 20th century, quantum mechanics was quite a tough pill to digest. But that trauma kind of made us into thinking that all the things we now think will one day be overturned, which might be the opposite, right? So we became quite agnostic in a sense about our beliefs, because, you know, that already happened once, that we found ourselves being completely overturned by nature. So you kind of learn from that, and you become a bit more conservative with your claims. Yes. Okay.
So Davide, I think we can wrap our conversation here, because we have to interrupt, but we still have some more points that we would like to cover, and for that, in the future we may meet again, and we may record another episode covering these topics, which I very look forward to doing. So I would like to thank you very much for your time, explanation, and it was great. It was very exciting, and also I think that I gotta say, spanning multiple topics within one talk is actually, I would say, nicer. let's put it this way. I like it more compared to only delving into one topic, which is again equally exciting. But again, thank you very much for your time. Good luck with your future plans.
Sure. Thank you. Oh, pardon?
Congratulations for your for the discussion of your thesis again.
Thank you for inviting me, and good luck with your podcast and projects.
Thank you very much. So this was Math and Beyond, the 20th episode. Thank you everyone for following along with us, and I will see you in the next episode. Ciao.